existed on Earth. What is the age of our cosmos then? Most people believe that our world is 13.8 billion years old. Our estimations concerning the existence of the universe are accurate. But no, since we created the Big Bang Theory, a description of the planet's evolution on this current timeline, the age of the universe is currently one of the most hotly debated problems in astronomy, and every time we seem to get closer to an estimated age, some new revelation appears and knocks that age out of the water. For example, new observations from the Webb telescope are testing our presumed paradigm. The Hubble constant. These new findings, however, tell us to make improvements to our standard paradigm instead of just proving our hypothesis to be incorrect. Check out the Hubble constant for more information. Thanks to astronomer Edwin Hubble and many others, we can use the Hubble constant, arguably one of the most significant constants in astrophysics, to establish the duration and development of the universe by knowing how quickly the cosmos is expanding. Since 1929, astronomers have been aware of the universe's expansion. Hubble's constant, sometimes known as h0, is the name of its present speed of expansion. There are two main approaches to estimating h0, and for 15 years, they have largely occurred with each other. This is significant. Here's why h0 is just as important to the standard version of astronomy as the speed of light is. Everything we know about the universe, including its age, size, and composition, is influenced by h0. In contrast to the speed of light, if h0 is changed, we get a different age for the universe. Different relative amounts of stuff, dark matter and dark energy, and so on. However, as h0 cannot be measured in a lab, it must instead be deduced from observations of the universe. Researchers have only been able to measure h0 by combining observations of type 1a supernovae with the redshifts of their host galaxy. When 1a supernovae burst, they all produced nearly the same amount of light. A 1a supernova's distance can be determined by evaluating the quantity of light it emits to us. How quickly an object is departing from Earth can be determined by examining its redshift or expansion in wavelength. When examining things in our local universe and then traveling outward to determine the speed of evolution of the universe, scientists employ multiple 1a supernovae as distance indicators. The cosmic microwave background, or CMB, is the focus of the other h0 method of measurement. The early universe was incredibly hot and dense, making it impossible for light to move around freely throughout space. This is known as the afterglow of the Big Bang. At that moment, observations from the cosmic microwave background, such as the concentration of both dark matter and dark energy, can be made using the CMB. These data can be used to deduce Hubble's constant, or the frequency at which the universe is expanding. However, as these two sectors have increased their capacity to determine h0, it has become evident that they do not concur. In a recent investigation, the first strategy produced a volume fraction that was 8% higher than the outcome of the second technique. Scientists are now wondering, are we overlooking something? It's possible that we don't comprehend the ambiguities well enough to explain why these two techniques differ, according to Wendy Friedman Sullivan, professor of astronomy and astrophysics at the University of Chicago. To quantify h0 using the first approach in 2001, Friedman oversaw the research. He is currently in charge of a new initiative to estimate it even more precisely. Another fascinating concern is whether it is unreasonable to anticipate consistency in these observations of h0. If so, the traditional system of astronomy, which assumes consistency, may be flawed. If so, this would prompt scientists to go on an interesting exploration for a different model of the universe. Friedman questions, do we truly understand what constitutes all of the radiation of the Big Bang? Are dark energy or dark matter's qualities evolving with time? Or is there a brand new particle type we are not accounting for? Despite nearly a century of astronomical calculations and measurements, scientific researchers are still unable to come to a consensus on the exact number of the Hubble constant. Over the coming years, scientists like Friedman will be attempting to find flaws in how each method conducts its analysis before potentially bringing up a methodological approach to the creation of the universe. The real number might show us new particles or a different kind of dark energy that it needed to complete our grasp of physics. A meandering trek undertaken by light from a distant supernova in the constellation Cetus may assist astronomers to put an end to this disagreement, according to recent reports made by scientists. In a few more centuries, a star erupted in the distant galaxy known as MRGM 0138. The light from that eruption eventually came into contact with a collection of galaxies whose gravity bent the light. Hubble's survey in 2016 revealed 3 bright spots in the galaxy cluster. The initial 3 points of light that emerged in this Hubble image, according to astronomer Steve Rodney, were merely a coincidence. When Hubble revisited the galaxy cluster 3 years later, it noticed that all the points of light had disappeared. Astronomers deduced that it was a supernova based on these observations, and they gave it the moniker SN Requiem. However, Rodney and his associates believed that the supernova could resurface in 2037 because some of its light is traveling far, caused by gravitational refraction. Astronomers anticipate that this supernova will resurface in the year 2037, which would mark a remarkable latency of 21 years for a supernova. The Hubble constant can be determined precisely by using the most recent latency to figure out the distance to the supernova's home galaxy. Supernova Requiem's host galaxy is farther away from Earth as time goes on, which results in a decreased Hubble constant and an aged cosmos. The precise date of the supernovas bring back to life might assist and settle the issue, nailing down a key cosmological parameter if the Hubble constant controversy continues into the 2030s. The Hubble constant currently varies between 67 and 73 kilometers per second per megaparsec, but that fluctuation leaves the age of the universe up to debate. The Hubble constant of 67.4 matches the commonly used age of 13.8 billion years. The universe could be older or younger than 13.8 billion years old, depending on the results of this supernova discovery, which would require us to reconsider our present cosmological theory and how it has evolved.